Hello, we're going to talk about energy. First off, previously we talked about momentum and impulse, right? So impulse is when a force is applied over a time interval and that changes the motion of an object. So remember, impulse is force times time and change in momentum. There's also a concept of work, not the one you're familiar with. And this is a force applied over a distance that changes the energy of an object. So remember, impulse was force times time. Work is force times distance. And work, we give the label of a capital W. And then force and distance should be familiar with. So let's take a look at a situation. We have workers lifting gravel using a pulley. That's what's happening here. Worker lifting gravel, pulley, somebody like catching it or whatever, grabbing it. They're applying a force over a distance. So force is whatever the weight of the gravel is, right? And then the distance is just however far up they're pulling it. So it takes twice the work to lift the gravel 2 stories instead of just 1 story. And that's because we're doubling the distance. So looking at this equation, if the force required is still the same, like they still have the same weight, but we increase the distance, that's going to increase the work required. So twice the distance means twice the work done. Now we can look at another example. This time, we've doubled the amount of gravel that we're lifting. So we're lifting twice as much. And so that means twice as much force to go the same distance. So twice the amount of gravel means twice the force applied means twice the work needed. Where before it was the same amount of force and gravel, but it was twice the distance, so that meant twice the work. So work done, there's kind of 2 main categories of work, either work done against a force, like the worker lifting the gravel, they're working against the force of gravity to lift the objects. There's also work done to change speed. An example is a club used to hit a golf ball that's at rest. So at first the golf ball's just resting there and then it's hit by the club, which is doing work on it. And that changes its speed from no speed to whatever speed you hit it with, unless you miss. And the work done involves a transfer of energy, either to act against a force or to change the speed. So again, just to summarize that all that on the same place and give you the units. Work equals the force times the distance. W equals F times D. And these work and energy have their own units called joules, and we give them a capital J. And thinking about the units of force and distance, right? So force is in newtons and distance is in meters. So joules are newtons times meters. Let's look at an example. How much work is needed to lift a bag of groceries that weighs 200 newtons to a height of 3 meters? So we have a force, right? Because that's in newtons. So that's the force, how much it weighs against gravity. And we have a distance, that height of 3 meters. So we can say that the work needed is that weight times, or that force times that distance. So that's 200 newtons times 3 meters. That's going to give us 600 joules or Newton meters. Okay, so that's what it takes to lift it 3 meters. But then the next question asks, what if it's twice as high that we want to lift it? And in that case, so that would change the distance to 6 meters, but we don't even have to redo the calculation. We can just say, okay, if it's going to be twice as high, the work's going to be twice as big. So instead of 600 joules, it's 1,200 joules. Now, work done over a time interval is called power. So it takes more power to do the same amount of work in half the time. And we can look at the equation and see this. So work done is on the top of a fraction where time interval is on the bottom. And remember, you can always double check this if you forget, but if a big number is on the bottom of a fraction, then the overall value is smaller. So a small number at the bottom of the fraction means the overall result is bigger. So if we're doing the same amount of work, but you do it in 2 seconds and someone else does it in 4 seconds, then you're using more power than that person. One way to think about this is an example of unloading groceries. Let's say you live on the second floor of an apartment building and you do the same amount of work if you walk the groceries up the stairs as if you run them up. But you use much more power to run them up the stairs. And that's because you've done the same amount of work carrying those grocery bags up to the second floor, but over a shorter amount of time, meaning the power required is bigger. Power has units of watts, which are joules divided by seconds. We have another concept, mechanical energy, which is the energy due to the position or movement of something. So let's look at one example of mechanical energy. Potential energy. So, typo, sorry. Energy, so potential energy is the energy stored in an object, based, not baked, on its position. And how that works is that it has the potential for doing work. So in our example of the construction workers and the gravel, the position of the gravel is changed by the work done to lift it up. And that change in position stores potential energy, gravitational potential energy to be specific. For example, the gravel could be dropped on some object on the ground to compress it. And that would be doing work on that object. And yeah, we'll leave it there for now. Gravitational potential energy, again, is energy stored in an object. And it depends on the work done against gravity. So this one is not just potential energy broadly, like the concept of the energy stored within like relationship between where objects are or how they're related to each other in space. But gravitational potential energy specifically has to do with the force of gravity. And so when we're looking at the gravitational potential energy, because remember, work is a way to transfer energy. So we actually can use the same relationship here where it's a force times a distance. But because we're looking at gravitational potential energy, the force we care about is the weight. And the distance we care about is the height, like however high off the ground it is. And yeah, sorry, I already said this, work equals force times distance. So we can look at this example of the construction worker, or more than one construction worker, and the gravel bags. So the weight is pushing down. And in our example, the construction worker was pulling the gravel up. So the height is like 2 floors upward. So the weight is mass times gravity. Height you can just list as h. And we get an equation here for the potential energy as mass times acceleration due to gravity times the height of the object. So this tells us that whatever position our object is in, and what if we know its mass, we know its potential energy. And again, this is, yeah, just represents potential energy. It just takes up less space. So pause here and see if you can answer this, but we'll talk through it too. So we have this ball and these different, I don't know, platforms, I guess you could call them. And we want to know which one of these balls has the greatest gravitational potential energy in its current position. And remember, gravitational potential energy is mgh, and we're assuming these balls all look the same to me for the most part. That one has an extra scribble. So we're assuming the mass is the same for all of them. And we know acceleration is the same for all of them, gravitational acceleration. So the only thing that might be different is the height, and we can see that actually no, the height is the same for all of these. So the answer here is D. They all have the same gravitational potential energy because they have the same mass and they are at the same height. So here's an example of an object that is lifted. Sorry, the example is here on the side. An example of an object that is lifted, giving it gravitational potential energy. So it's pulled up to some height above the ground. That gives it potential energy, gravitational potential energy. And then it's released and it does work on this stake in the ground when it hits it. But from this point up here where it has some potential energy in between, once it's released, it gains some velocity, and that velocity is what goes into the kinetic energy. So the kinetic energy is the energy of motion. Because also if an object is moving, it is capable of doing work. So kinetic energy is 1/2 of the mass times the speed, which is the same as speed squared. And here's just in variable form, kinetic energy equals 1/2 mv squared. M is mass, v is speed. And you can also, it's totally fine to also call this v velocity. It's just that kinetic energy doesn't care about vectors, like it doesn't care about direction of the motion. So what happened here was work was done to change the potential energy of our object. And then it was released from its stopped position and it got some velocity, which turned the potential energy into kinetic energy. And that kinetic energy did work on the stake. So that was kind of an example of transitions between potential and kinetic energy. But here are some different snapshots of a pendulum. So it's just, a pendulum is like maybe a object hanging from a string that swings back and forth. So that's what we're looking at here. It is at this certain height here indicated by the green line. So at that point, it's not moving. We know that because it doesn't have this little vector showing us that it's moving. So there's no kinetic energy when it's not moving. And this is a maximum potential energy. This is as high as this pendulum is going to go. So if it's at its highest point, it has its most gravitational potential energy. And then here we see it's moving down. So it's going to a lower point. So that potential energy is decreasing. But it also has some speed now. So it has some kinetic energy. So the potential energy decreased, but the kinetic energy increased. And then down here, we're at our lowest point, and that is also when our velocity or speed is the fastest. So lowest point means no potential energy. Everything is in kinetic energy. And then we're back to pretty much the same point, just on the other side. This is our maximum height point again. That's when the potential energy is at its highest and kinetic energy is at its lowest. Let's talk work energy theorem. So a change in kinetic energy requires work to be done. So as we saw with the example, work was done to raise the gravel. I think that's what it was in that previous one. The gravel, and then it was released, and that caused generated the change in kinetic energy. Another example is a car trying to brake quickly relies on the friction force between the road and the tires. And that force acts over a distance to bring the car to a rest. An interesting bit of information from your textbook. Due to the material that makes up tires and roads, the road can only provide a limited amount of force to slow a skidding tire. Remember, we talked about how friction depends on the two objects that are in contact with each other. That means that a car traveling twice as fast is going to leave longer skid marks on the road, 4 times as long, actually. The same amount of force, which the maximum friction between tires and the road, must be applied over a longer distance to reduce a faster speed. So I thought that was interesting. I hadn't really thought about skid marks on the road very much personally. So yeah, if you are solving a mystery and have skid marks on the road, you can measure them, figure out how fast a car was going. So this is connecting the work done because the work is the change in the kinetic energy and it's the force times the distance. So we can actually use the force applied over a distance, which is what this example was of the skid marks from the tires, and set that equal to the mass times the velocity squared. So in this example, we're saying changing kinetic energy, but down here we're seeing only one. So that means we're assuming that we in this case, we end with no velocity. So like at one of our times, we don't have any speed. Sorry if that was confusing. So energy cannot be created or destroyed. It may be transformed from one form to another, like kinetic to potential, potential to kinetic, but the total amount of energy doesn't change. Let's look at this with this example here for this circus diver. So he's initially up here at the maximum height. He's not moving yet, so there's no kinetic energy, and we have our maximum potential energy. And it doesn't have the units here, but these are in joules because it's energy. So then he jumps down. That means his height is decreasing, so his potential energy decreases, and we see that it's from 10,000 to 7,500 joules. But he also has some speed now, so he has more kinetic energy than before. But if we look at these, just like this one snapshot and up here, if we add up the 7,500 and 2,500, we get 10,000. So the total, which is kinetic plus potential, is the same in both, well, in every position, actually. Let's keep looking. So now he's at the middle point, and we kind of have an even split between the potential and kinetic energy. And then as he goes down, he's going faster and is closer to the ground. So there's less potential energy and more kinetic energy. Until finally he's on the ground, or almost. His potential energy is the minimum, his kinetic energy is the maximum, and we're just at the opposite of this peak point. And then he's jumping into a tiny little bucket. So that part I feel like is not actually realistic. But the rest is that the total energy is constant, and it just changes forms. It's either all potential and no kinetic, or some split between them, or all kinetic and no potential. Okay, that's all for now. The next lecture is going to show you some examples. Have a good day.